All righty. Oh no, the title is incorrect. Okay.
It might be worth posting the URL to the live stream, because when I click on the link, I don't get that. I just get the SPLS YouTube.
Yeah, they're posted.
Oh, they are posted somewhere, are they? Where are they?
Both on the channel and next to the name of the speaker.
Ah, there, right, yeah.
But
Excellent.
that's probably not very intuitive.
No, that's... why does it say Kwan Hoon Choi? When I click on the link, I don't get that.
Oh.
Sorry, that was me playing it.
I don't know. I think this will change once Neel starts sharing. Neel, you want to start sharing your screen?
Sure, I'll start doing that.
We're going to start in a minute.
Let me make sure that it's all set properly. Yep. Okay, is this visible to everyone?
Yep. Looks like YouTube is catching up. It's just a little bit slow. All right, we're going to get started now. So everyone, please welcome Neel Krishnaswami. We'll talk about Adjoint Reactive GUI programming. Neel, if I'm correct, you're happy for people to interrupt you?
Yes. If you see something confusing or you just want a clarification or just want to ask a question, like feel free to interrupt me at any time. There's no sense in being like confused for half the talk. Yeah, I guess, should I get started now or?
I'm just going to say that if people have questions, they can post them in chat in the SPLS Zulip channel. There's a link into the announcement, and I will relay the questions to Neel.
Okay, thank you.
Right.
I'm sort of in full screen mode, so I can't see Zulip right now.
Yeah.
Okay. Well then, yeah. So thank you all for having me. I looked at the list of attendees, and it's always nice to see a whole bunch of familiar faces, and it's also exciting to see a whole bunch of new ones. So I'm actually like really happy to be here. And what I'm going to talk to you today about is some work that appeared in FOSSAX this past year about a paper we called Adjoint Reactive GUI Programming. And this work was done in collaboration with Christian Grauland, who at the time of writing was a PhD student at the IT University of Denmark, and has now since finished his PhD, and with my PhD student Dima Samosvanchev. And so the basic thing we're trying to do is we're trying to ask the question and also answer it: how should we program programs that have graphical user interfaces? the answer is we need to look for monoidal adjunctions between functor categories. And the purpose of this talk is to convince you that this is not a completely ridiculous way of answering the question. And so what we want to do is, before we get into like any semantics or type theory, it's actually good to know sort of what the actual program, what the actual problem is. And so we're going to look at a language that's much more difficult than category theory. We're going to look at a little JavaScript program. Or something approximately like JavaScript. And so if you wanted to make a button in JavaScript, what you would do is you'd write something like, okay, I'm going to create a button object by calling a method to create a button object, and then you'll invoke further methods to update its state and set any properties that you want of it. So we've invoked a button and we've written hello world on it and we've turned it blue, and now you can see my ASCII art button. And because that's not quite ASCII art, it's like hand-drawn art. So this is basically what building a little widget tree in JavaScript is like. So you have a DOM, which is a big tree representing your document, and by calling methods on it, you can add things to this tree or modify them. And the tree itself is actually a stateful gadget. So here we have a program. So we created our button right here, and now we've set it blue, and we'll have a blue button. And if we perform further state modifications on it, like maybe we turn it red, then the widget will actually change color. It'll go from blue to red. This looks like, and you should actually think of it as, it's just an imperative update that you happen to be able to observe by looking at your screen. Okay, so we have imperative trees that we can mutate. Are we done yet? And the answer is no. There's more to GUI programs than just building trees and modifying them with assignments. And the reason is the I part of GUI, the interaction. So we write these programs so that we can interact with a computer and have things happen. And our interactions are sort of extended through time. Like you do something, and then a little bit later you observe something, and then a little bit after that you do something else. And so there's like this extension of this program throughout time. And so what we've got here is we've created a blue button. And then what I do is I'm going to add an event handler to this button. I say to B, I'm going to invoke the onClick method, and I will pass the onClick method what's called a callback. And what this means is that whenever the button is clicked, we want to run this function. And so usually the way these things work is you're passed a little bit of data which tells you all about what just happened in the current event, and then you do something imperative in response to that. And in this case, what we're going to do is we're going to invoke the setColor method again, but we want it to be red. And the thing about this is that when you call this, the button is not going to immediately turn red, it's going to remain blue. And it's not going to turn, it's not going to turn red until we click on it. And so if you think about what's happening here, we have a stateful object, and now we're thinking about its life cycle through time as well. So our button is going to start off blue, and it's going to remain blue here, 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 and here, and then eventually at time n we're going to somebody clicks on this button, and then it turns red. And so that's like sort of the standard model of GUI programming. Like it was actually invented the year I was born by Trygve Reenskaug, and it's called Model View Controller, and it's really hard to use. Like if you've done much GUI programming, you'll generally have less hair at the end of it due to how much you've pulled out. And part of what makes it really hard to work with is that it's very difficult to reason about these programs, and things that look the same can actually be different. So here's a slightly different program. And what's different about this program is that when this object was born, I didn't make it blue, I made it red. And then I give it the callback that says, well, when you're clicked, turn red. And so you say, okay, well, that didn't seem to do anything. Then you might wonder, well, could I instead just create the button and then turn it red? And are these two programs the same or different? And if you run it in JavaScript and you stare at your screen, they'll look exactly the same. And the only time that you'll notice a difference is if you write some more code. So right now, what we've got are these two programs, and we'll say, and let's say that at time 0, it starts off red in both cases, and at time n, both of these programs are clicked. So now let's think, what will happen if immediately after writing all this code, I change the color to blue? And so now what you'll see is that this program on the left, which was initially set to red and then set to blue, it's going to start off blue, and then it's going to remain blue through its whole life. Whereas the one on the left, the one on with the callback, it's going to be born blue, and then it's going to stay blue until we click on it, at which point we've changed the color of the object changes. And so now we have an observable difference between these two programs, and we couldn't actually observe the difference until time passed and the program was and the button was clicked. So we not only have to think about these things as stateful gadgets, but as stateful gadgets that are extended through time, and that's kind of tricky. And so what we can do is, to summarize this, what we need when we're writing GUI programs is some way of thinking about state. We have a blue widget and we can change its color and we get a red one. And we also need to be able to think about time. So if we say, turn the color red when the button is clicked, now you have to think about the extension of this value throughout time. And so this means that if we want to reason about the typical sorts of GUI programs that people write, we need to be able to talk about space and time. And so how do we do that? And since I'm a type theorist, I have ready answers to both of these questions. So I need to think about state. Well, I'll break out linear types. And I need to think about time. I'm going to crack out temporal logic. And so what we can do is we can say, well, our linear types will tell us how what the state of the program looks like, and we'll add temporal modalities to this linear type system in order to talk about how the state changes through time. And that, in a nutshell, is the approach that we take in our paper. And so, okay, I can say that, but what does it actually look like? And so here's the two basic operations in our API. So we would need to be able to create widgets, and we need to be able to destroy them. So if we create a button, you may click it for a while, and then at some point you've transferred your entire bank account to Bitcoin entrepreneurs, and this button is no longer necessary, so it can be freed. And so what we're going to do is we're going to say here with this first new widget, it says, when I invoke this function without any arguments, I want to create a value of widget type. And the thing we'll see here is that this is linearly typed because we have the ability to create and destroy widgets. So our new widget functions a bit like malloc in C programming. We invoke new widget, and we've gotten ourselves a fresh widget, which has never existed before in the history of this program execution. And we can use it as long as we like until we're done with it. And then we want to destroy it with a free widget call. And linearity turns out to be really important for modeling these kinds of stateful APIs, because if you called the new widget and then called free on it, you don't want to have the ability to refer to something that's been deallocated. And linearity, which tells you each variable can only be used once, that sort of exactly captures this single use nature of stateful programs. But that turns out not quite to be enough, because when you create a widget, you actually care that one widget is different from another. And if you have two buttons, they're actually different buttons. And so what we do in order to track the identity of things in our type system is we add like some static identifiers, so that if you have like widget I and widget J, your type system knows that they're actually different from one another. And then anytime you have these kinds of indices, you generally need quantifiers as well. So when we call new widget, we call new widget and it tells us, I'm going to give you a fresh widget and it's going to have some ID. You don't know what it is. All you know is that like it's probably different from anything else. And then when you call free, you want to be able to call free widget on any widget at all. And so we want to universally quantify over all of these identities. So we need to be able to talk about specific widgets in our type system, and in order to be able so we need to index our widgets with their name, basically. And then once we have these names, we need quantifiers in order to manage them. So that sounds okay. So you might be thinking, okay, well, can we actually write programs like this? And the other thing that you'll notice when you actually write a GUI program is that our widgets are all stateful, but there's a lot of the parts of the program which aren't linear at all. So like colors and numbers and strings and all the data structures we use in functional programming, we're happy to duplicate those. We really only care about linearity for the things which sort of represent state. And so what our API does is we support operations like set color. And I guess I also spelled it in 2 different ways because I'm an American who's lived in the UK and no longer knows how to spell. So what we've got here is a set color function, and we need to give it a color, and we need to give it a widget, and it'll give us an updated widget. And so what we can do is we need to be able to say you can use the color red as often as you like, but the widget itself has to be handled in like this linear fashion because it's getting destructively updated.
Can I ask a question, Neel?
Yes.
Just a silly thing. On your previous slide, you had this type I. What was that?
That's just the unit type.
Oh, all right.
So the idea is let me actually just draw on my slide here. You would write something like new widget. So this naturally looks barbarous if you're a Haskell programmer, but I've programmed in ML too long, so it feels natural for me to write parentheses at the end of a 0 argument function.
Thanks.
Yeah. While we're chatting, I'm wondering about the status of the IDs when it comes to being intuitionistic or linear. I guess that's back to the slide you're on.
Yeah, so all the IDs, they're all duplicable. They don't have any sort of runtime significance. They're only static IDs. So this is like sort of a first order logic over this linear nonlinear system. And since people were asking about the relationship between what's linear and what's nonlinear, if you see most presentations of linear logic, if you want to be able to duplicate things, you usually write this exclamation point. So if you want a color that you can duplicate, we write bang color to indicate this is the type of colors that can be duplicated at will. I'm writing it F color because I'm using a slightly different presentation of linear logic, which I'll get to in a minute. Sorry, let me back up. Yes, and so the point is that once you have linear state passing, like here, you can implement this kind of thing with actually just an assignment. So the set color operation in the programming language, which some of my students are implementing, it actually implements this as just an assignment. It gets fast a color and it gets a widget, and then it invokes the underlying like widget.setColor method. We're able to have a sort of semantically sensible API that nevertheless looks just like the low-level implementation you would have expected. then the other thing is this F versus bang thing. So the F is probably very familiar to Phil Wadler because it's something he did a long time ago with Nick Benton. He had an alternate presentation of linear logic, which had a functional language and a linear language on a equal footing. We'll see the details of that in a bit. I personally think this style ends up working a bit better for programming languages that mix linear and normal functional programming. Okay, so far you've seen how state passing works and like how state updates work. It looks like state passing style in a functional language, but you can actually implement it with assignments. But we talked a bit about time. And so now what we can do is we can talk about operations that will expose time in in this language. And so when we click on a button, the way that we expose this in our API is we say, all right, if you give me a widget, then I will give you that widget back, and then I'll give you a little notification of when the click actually happens. And so this diamond should make you think of temporal logic. You should read it as eventually. Diamond A should be read as eventually A. So for a click, you get the widget back, and you get something that represents a unit whenever the click actually happens. And similarly for key presses, you say, okay, give me the widget, I'll give you the widget back, and then eventually I'll give you a character. And eventually you're going to get whatever character eventually gets pressed. Okay, and so this little diamond thing, it tells you at some point in the future, you'll get a character or you'll get a unit or whatever. And you also, just like we had with IDs, we also need to sometimes talk about specific times. And so what we do here is we introduce this new connective, A at t, and it means that you get an A at the time t. And as a result, Diamond A sort of can be understood as saying, Diamond A is sort of equivalent to saying there exists a time at which you'll get an A. And so even though this primitive notion of an event happening at a certain time is like really the more primitive concept, it turns out to be useful to be able to have Diamond as well in the API. And just as a note for the logicians in the audience, like this A at t is an instance of what's called hybrid logic. So this is a hybrid temporal logic. So now we're able to say, okay, well, eventually I'm going to get an A. That means there exists a time t at which I get that A. And if I happen to know that I have an A at time t, I can sort of forget that information and just know that it's going to have, I have an A at some time. Okay, and the reason that we needed these IDs and these time indices is because when you have a widget, you need to be able to split it apart and put it back together at different times. So in our example, back here, let me go back one more so you can see it here. What we've got here is we're setting the color, and this is telling us I want B to be the same until the event actually happens, at which point I want to perform this action. And so what we want to do is we want to be able to perform actions at different times. And so and we want to be able to perform them on widgets at different times. And so we're going to add two more operations. And this is pretty much it as far as the API goes. We want to be able to split a widget into its timeline. So if you have a widget, you should be able to break it up into a widget starting at time t and the state, the ownership of the widget from now until the time t. And similarly, if you have like sort of the prefix of the widget's history, and you know that the widget resumes execution at time, sorry, not resumes execution, you resume ownership of the widget at time t, you can put it back together and say, well, actually, I have ownership of this widget starting right now. And so maybe I have a picture of this. Yeah. And so the idea is that when we have our widget, it is a piece of state that's extended through time. So we have a widget and it has a state at time 0, a state at time 1, a state at time 2, all the way out into infinity. And when we split our widget, we get a prefix, which is ownership of its states from now up until time t minus 1, and then the widget at time t, which is everything else in the future. And so if you've done like conventional FRP programming, you often program stateful things as streams, where you say, I have a stream of values, and this stream can be split into two parts, like the head of the stream and then the tail of the stream, which is a stream starting one step in the future. And what we're able to do now is we're able to split our widget into two parts. And you can see why we need this identity. Because if we have a prefix running until time t, we need to be, when we put it back together, we need to know that we're putting a widget with its own prefix together. You can't take two widgets, chop them apart, and then have like some sort of Frankenstein graph where I own a widget. I have a widget where I own one thing from time 0 to t and something else entirely from t onwards. And so making sure that this I is the same in both the prefix and the widget means that we put things together sensibly.
Can I just ask a little question?
Yes.
So the initial intuition I had for at was that was, well, widget I at time t meant a widget at only time t, but you seem to be now indicating that it means all t's, it means now and every time in the future. Yes,
so the point is that a widget is really a state extended through time. So you imagine you have like some DOM tree and you're performing some updates on it. So your widget is going to represent all of those states. So it's like the entire history of that widget. Okay. And so widget at t means you have an entire history starting at time t.
Right. Although obviously you can't inspect the times that are in the future. That's right.
So so all of these quantifiers like IDs and times, you can't inspect any of them. Like they're purely a compile time notion. So if we look back here, so with the join, we're putting together a prefix and its widget at time t in order to get a widget right now. And the reason for these IDs and times is basically just to ensure that we stick things together at the right times in a statically checkable way. Like the actual implementation doesn't have any sort of clock in it built into it. It just sort of hitchhikes on the event loop of the GUI toolkit.
I guess in some sense, the actual inhabitants of this data type are not even part of the program; they're part of the environment.
Yeah. There, unfortunately, there's no introduction and elimination form for widgets. All you get is like the HTML5 spec.
Right.
And that's the lucky case. I guess you get like Win32 or GTK if you're less lucky. So that actually brings up a good point, and we'll see this in a little while, which is that a lot of these the semantics for these like the way that we approached this problem was actually to think about the semantics of a widget and then try to work out like where its semantics should live. So we sort of knew what a widget meant, And then we said, okay, what category does this gadget have to live in for it to make sense? And then we looked at the structure of that category to figure out like what the programming language was. But like that's sort of a backwards way of approaching things. So I'm going from the programming language towards the semantics. Okay. So you can ask, okay, well, I've asserted a lot of things. What do these programs actually look like? And so what I want to do is I want to show what a small program in our language actually looks like. And so what this program does is you give it a widget. Oops. You give it a widget and you give it a number, and then that number is going to get incremented by 1 every time you click it. You click this widget. And so what we're going to do is we're going to say, okay, well, initially we're given a number n and we're given a widget. And so the first thing that we're going to do is we're going to set the text of our widget to whatever the string representation of the number is. And then what we want to do is we want to wait for a click on this widget. So that's what we're doing here. We call onClick, and that gives us the widget back, and it gives us this event that's going to happen in the future. And then what we do is we say, okay, well, what time does this event happen at? And we're told, well, it's some abstract time t. You don't know much about it. And we say, well, we don't know exactly when it happens, but we can call split on this widget, and we can say we can logically divide the ownership of the widget into the part that lasts from now until time t, and then the stuff that from t3 from time t onwards. And then what we'll do is we'll say, okay, at that time t, recursively call this function, this time with n+1. And so now this W4 prime is going to have a counter of n+1, and it's going to wait for the next click to be updated. And now what we can do is we can say, okay, we have what we want starting at time t, something that increments its clicks, so we can join it on to what we have now, and now we have a widget that whose state will be whose displayed state will be incremented by 1 on every click. And so if we
go back for a minute, Neel.
Yep.
I'm just slightly confused by 2 things here.
Yep.
One is that when you do out,
yes,
you want a sorry, out gives you the time t at which this is
Yep.
going to happen, and then
Yep.
you do a split.
Yep.
And split seems to just, without being told, magically pick the same time t.
Yes. So basically, Hindley-Milner type inference can figure out which index to choose. In fact, you don't even need full Hindley-Milner. So the type of split is going to be something like, for all IDs, for all times, if you give me a widget of I, you'll get out a prefix of I running to time t, and you'll get a widget of I at time t. And so what'll happen is you call split, and you don't know what I or D are, and what I is determined by the argument. And the sort of the point is that, like, you find out okay, so this out, sorry, I'm going to add outs as well. So out takes a diamond A and gives you an exists T A at T. And then what'll happen, sorry, I'm just getting into the details of type inference a little bit. So we learn when we unpack this existential, we get a name for T, for this time that the event happens. And then when we make the recursive call, we do it at this time T, and that, when we call join, tells us that split must have been invoked at splitted at time t.
If I wanted to, could I also pass t? Could you redesign split to also take t as an argument?
Yeah, sure. You could make all of these things. You could make all of these things explicit if you wanted to. It's just a nuisance to do it if it can be inferred.
Okay, that makes sense. And then just to check I've got this right, when you do this let for w prime 4, could I leave that at t off the right-hand side and instead put it where I'm doing the join on w prime 4?
Yes. So the thing that you could do if you wanted is let me just move this bit here. You could move this whole expression right here. Oops.
I didn't ask that. I asked something different. Could I bind w prime 4 without that at t? And then
no, that wouldn't type check. And the reason it wouldn't type check is because this w prime, let's see, yeah, this is actually w prime 3, I think. This w3 prime, it's a variable that's only available at the time t. So if you try to use it at a different time, you'll get like a type error saying you want to use this variable now, but it's only available at time t.
So I'll just note I'm slightly confused because you've written w prime 3 at t.
Yes.
At one point, but the next point you write p w prime 4, which has the at t inside of it. It looks like those two uses of w prime 3 and w prime 4 are of a slightly different type. Is that correct?
W3 prime and W prime 4 do have a different type. Let me show you the next slide because this has the contexts in it. So like when all the variables are available is sort of visible here.
There is also a question in chat about the third line, which is let parenthesis t and then at t.
Yes.
The question is like, what does that mean? Is that linear pattern matching? Is it saying like matching this at time t?
Yes. So let me explain this bit as well, and then I'll move on to the contexts. So what's going on here? So out gives you something of an existential type, and so this purple thing right here is is like an unpack. Is the variable of the unpack. So you have an existential type, and that's the thing you're binding right here. And now what we've got here is actually, since E has the type diamond unit, the type that we get is like unit at time t. And you're allowed, because well, you're allowed to deconstruct that unit, even if it's in the future. And that's just the pattern matching for pairs and for tuples and singletons in the future. So you can it's basically like unit elimination. So so for units, there's an elimination form, let unit equals E1 and E2. And if you happen to know that your unit is in the future, what you're allowed to write is let unit at t. And that just says, okay, this unit is going to be ignored henceforth. So a lot of this is stuff that you have to be a little bit more explicit about because you're working in a linear type theory. So even if you've got a unit, you have to explicitly eliminate it because otherwise it hasn't been used linearly. So there's a degree of bookkeeping you get from the linearity, and some of that is showing up here. So now let me...
Presumably there's another little typo there. It should be split W2.
Yeah, it should be split W2. That's right. Oh, well, doesn't matter. I'll just go on. Okay. And so now what you can do is you can see how these states evolve. So initially, W0 is going to be a widget with ID identifier I. And then once we do the set text, what we're going to get is that W1 is again a widget I. It's just been, it's state passing style. So the updated state is now bound to W1. And now when we call onClick, what we're going to get is we're going to get W2, which is our widget, back again. And we're going to get this unit I, or eventually I, which says at some point in the future, the click will happen. And now when we unpack this out, what's going to happen is we learn the time t that the event is going to happen at. And then when we do the split, what we're going to do is we're going to get the prefix, which runs, which for the state, for the widget I, that runs until the time t. And then W3 prime, it's also going to be a widget I, but it's only available at the time t. So only in the future can you use W3 prime as a widget. And so that's what's happening here on this line right here. So we want to produce a widget by recursively calling the counter. And so we're calling count on W3 prime, but because W3 prime is at time t, we have to annotate it and say, don't run this straight away, run it in the future whenever you get around to it. And so now you'll get back a widget at the time t. So this is actually at t. So sorry. So this expression right here is going to be a widget of I, and it's going to occur at time t. And then this thing right here is going to ensure that the whole expression is now a widget at time t, but that's available for use now. And now we can put these together with join.
I hope you're planning on filling us in on the typing rules for these at keys in types and in terms.
Yep, we're about to get to that. Like the kind of the high level point is that this looks like a functional stream munging program, just a bit more verbose with a whole bunch of bureaucracy for times.
Are all the times you can talk about in the future? I'm just trying to see how guardedness is going to work.
Yeah. So the answer is there. You don't know. So it's going to be now or in the future, because when you call on click, you don't know when that click is going to happen. So it's in the sense of temporal logic, you're only talking about future times. And as for guardedness, we set things up so that it ends up working a bit like the modal mu calculus, where the inductive types sort of talk about liveness properties, and the co-inductive types sort of talk about safety properties. So guardedness is syntactic the way it normally is in order to give you like sort of the extra safety liveness properties. It's not like in step indexing or something like that, or where all the recursive types collapse.
Well, given that that's guarded on, what is it guarded on the times?
It's not exactly. It's not guarded. Sorry. There's two senses of guarded at work. I thought the sense that Connor meant it in was in the sense of guarded recursion, like you would see in his work with Bob Atke on co-inductive programming. And we are not doing that. Instead, but we do track when variables are available, and you're only allowed to use them at certain times, that in order to ensure that like you don't try to do a future action right now.
Yeah, I mean, so the thing I'm concerned about is what happens if the time that comes out of the out is the present. And so count n is defined to be count n plus 1.
So in our semantics, we don't care. I think in JavaScript, like all the events are promised to be in the future.
Right. So is this something where you can leave that to physics?
Yeah.
Neel, just
Yes.
before you leave this slide to go on to typing rules, a notational point. So in your let patterns for binding times that are existentially quantified in lines 3 and 4, I guess it might help particularly students, but also me, if I understood the first occurrence of T as binding and the second occurrence as a dot pattern a la Agda, saying, I'm another time which could be bound, but actually I'm already spoken for. It's the time you first thought of.
Yes. So
there's a lot of unification constraints hidden in those patterns, which would be helpful to tease out at some point.
Yes. So this is actually something we went back and forth on many times.
Okay. Okay.
Because this T is a binding occurrence, and these two are not binding occurrences.
Yep.
And if you remove them, everything gets much harder to understand. And if you put them in, like you have this weird mix of binding and non-binding. So we're not totally happy with any of it.
So dot patterns in Agda are one way of legislating for that, I guess.
Yeah.
Just a thought. Thanks.
Yeah. No, I think that's a good idea. Okay. So let me move on a bit. So now what we can do is we can actually run this program. And when you run it, what you'll see is that you've got a button. It starts off at 0. And then every time you click it, the counter gets incremented by 1, or the displayed counter gets incremented by 1. And so this sort of works the way that you want it to. And you can, but I don't have time to talk about, like, the fancier things that you can do, like creating widgets that create other widgets and so on. Okay, so now we get to what Phil asked for, which is the type theory. And so this is, to summarize, a first-order linear nonlinear calculus with hybrid linear temporal connectives. Okay, so what does that mean? And so the linear stuff is sort of managed by what's called the linear nonlinear calculus. And this was a presentation of linear type theory that Phil and Nick Benton invented in the mid-90s. And the idea there is to have not one calculus, but 2. So you have a functional language which works just the way that you're used to. So variables can be used as often as you like. You do the Curry-Howard reading as intuitionistic logic. Everything is normal. And then you have a second category, which is linearly typed. So you have your linear function space and your tensor products. And then what you do is you say, well, I have these 2 universes, and the way that I connect them is with an adjunction. So I have a way of taking an intuitionistic type X and embedding it into the linear world. And conversely, I can take linear things and embed them into the intuitionistic world. So you can think about this G of A right here as linear things that are safe to duplicate. And you can think of these f of x things as intuitionistic values that we're just going to pretend are linear. And so what this means is that in the nonlinear world, you can write functional programs the same as always. And in the linear world, you can work in like sort of a very pure state passing style, and you have access to the nonlinear stuff when you want it. So it turns out to be like a really nice programming language for doing linearly typed programming when you have like a mix of some values are linear and some are nonlinear. And it's in this linear world that we put all of the GUI specific types, and we add our hybrid temporal connectives. So we have our A at a specific time, T, and we have like our diamond, which says eventually at some point in the future. And then the rules for this type theory actually turn out to be extremely straightforward. There's a lot of judgments because anytime you have a first order quantifier, you need like a judgment for all of the index sorts. And then we're going to have a judgment for the nonlinear things. And then we're going to have another judgment for the linear things. And so you can see here that the index terms refer to the index variables. The nonlinear terms can refer to nonlinear variables or index terms. And linear terms can refer to index variables, nonlinear variables, and linear variables. And then, because our linear terms are also temporal, we also have yet one more judgment, which says T is a linear term that gives me an A at the time I. And so there's a lot of judgments, but it works out that all of the rules end up being extremely straightforward. So the rules for intuitionistic typing are literally the standard rules for the simply typed lambda calculus, well, the first order lambda calculus with nothing exciting or interesting going on. Like the only place something non-standard happens is in the introduction rule for this G of A connective. And it says, I am allowed to treat this linear term T as a nonlinear term when I'm able to type it in an empty context. So any closed linear term can be duplicated as often as you like, so it's safe to treat it as an intuitionistic value. And for the linear typing, it gets a little bit more complicated because we have like a context with two sorts of variables. We have one sort of hypothesis which says I have ownership of an A right now, and then we have another sort of hypothesis which says X is an A at time I from now. But aside from that, like all of the rules for linear types seem to work out in a very straightforward way. So we can refer to a linear. Sorry, I heard a question. What?
If you just always wrote something in the form A bracket, I close bracket, could you just have A bracket 0 close bracket?
Yes, you could. What would end up happening is you would end up writing a lot more bracket zeros.
Right. Should we understand that omitting the time just defaults to at time 0?
Yeah, it means right now.
But there's no difference between writing nothing and writing bracket 0, except I guess you don't have, the 0 exists because you only allow i's there rather than constants.
Yeah.
So I can't say at time 42 something happens.
Yeah, so semantically you certainly can do that, but that's something that for implementation reasons we wanted to forbid. So like older FRP systems sort of wake up on every time step. So you wake up on every time step to see what you need to do, and then you do it. And then you go back to sleep. So like all the sort of modal FRP systems that I've worked on have this property, and that's quite inefficient because you can sort of pull the time. And because the potential for pulling exists, you have to implement it that way. But in this system, because you can never refer to a specific time, it's safe to implement things with a sort of quiescent style where you never do anything until the event actually happens. So one is push and one is pull, and I can never remember which is which.
Okay.
So yeah, so most of these rules for the linear type stuff are just work the same way as in Phil's 96 paper or in Girard's 87 paper for that matter. And the bit that's a little bit less familiar is the way that these adjunctions work, these adjoint connectives work. So if you have an intuitionistic term of type G of A, then you're allowed to sort of execute it, and you'll get an A in the empty linear context. And if you have a intuitionistic term of type X, you're allowed to make a linear term f of X, and it doesn't need any linear resources. And if you want to, if you have something of type f of X, then you can sort of let bind it in order to get a variable of type X to use as often as you like. And it ends up working out that the exponential of linear logic is encodable with this FG thing. And then what happens is that like these diamonds, these eventuallys, are sort of a standard S4 eventually monad. So it's monadic, but it's not like monadic in Haskell. It's a non-strong monad. And what that means is that you have an introduction form which looks like the return in Haskell. If you've got an A, you've got an eventually A. But when you do the do notation for it, if you have something of type diamond A, that means eventually you have an A in the future. You are allowed to use the A to produce something else of type diamond B. But the thing that distinguishes it from a strong monad is that this X is the only variable that you're allowed to use. And the intuition is that you're waiting for this diamond to happen, and you don't know exactly when it's going to happen. And because you don't know exactly when it's going to happen, you don't know if any of the variables in the linear context will be available then. And so we're able to write this down, and it ends up being implemented a bit like promise pipelining, if you know how promises are implemented in JavaScript. And now here comes the bit where the temporality sort of actually matters. So if you have two objects, one of type eventually A and one of type eventually B, you might want to wait for one to happen. You might want to ask which one happens first. And so we have a select primitive that says, well, run T3 if the diamond A happens first, and run T4 if the diamond B happens first. And so what we're doing is we're saying wait for the first one to occur, and then branch on that. And so this turns out to be implemented, sort of like a select primitive, like you would use in like a concurrent programming language. And if you read it as a axiom of temporal logic, it's the axiom that expresses the linearity of time. So it says if you have something eventually A and eventually B, then one of them will happen first. So eventually you'll either get an A and still have to wait for B, or you'll get a B and you still have to wait for A. And so then, okay, now we're almost done with the type system. We also have the ability to manage these hybrids. And just like we saw up here, we have to be careful about when the variables are, which variables we're allowed to use. We're only allowed to use variables at the correct time. So if we want to have an A at a time I, we're only allowed to use the variables that occur at time I. So if we have any variables that occur at different times, we're not allowed to use them. And similarly, if we have something that we know will become available at time I, we can let bind it and to a variable that does become available at time I. And that is pretty much the entire type theory. And the only sort of question you might ask is, why do we need both diamond A and this A at I? Isn't diamond A just this existential thing, exists in I, A at I? And the answer is, it's hard to implement type inference if you have them both. Okay, I've sort of run out of time for the semantics, so I will skip ahead to the end to see if there are any questions people have. So you can read our paper if you want to learn about the denotational semantics of this. And sort of the high level takeaway is that there's a lot of semantics going on and a lot of nice type theory even in something, as mundane as a GUI program. So, beautiful models abound even in like, what seem like the grungiest of programs. So it was sort of a real pleasure to come up with a system where, all the type theory and semantics sort of works in a canonical way, and we know we can implement it in like sort of the way people have implemented GUIs for 40 years. So thank you all.
Thanks for your talk. I think we can all clap. I suggest we take questions and a small break in the Gather server. So I'm going to post the URL in chat, and we'll resume in 15 minutes.
Okay, are you posting it in the Zulip chat?
In everything.
Oh, okay.
It's in SPLS. Almost, it's like, and the SPLS Zulip in Zoom and